All right, good afternoon, everyone. So we just have one more slide to cover on Unit 6, and it's just to briefly discuss a topic which will show up later in the next Unit 7, and it is the topic of constrained optimization. So the idea here is that until now, we've been considering our adjustable parameters as being unconstrained, meaning like any real number for the intercept, any real number for the first weight, the second weight, and so on. But in some situations, you might have some constraints on them. For example, maybe you wanted your intercept to be positive or something like that. So in general, there's a lot of optimization problems that show up with this form where there is some sort of constraints on the variables you're designing. And those constraints might be equality constraints. So this says here that some function of those weights, W, which we're designing, equals 0. And in this case, we actually could have L different functions of them. Little l going from 1 to capital L. So we have a bunch of different functions which must exactly equal 0. And it's enough to say equal 0 because if there's some other number that you wanted it to equal, you could just move that into the definition of this function. So you can always write an equality constraint this way. But you can also have an inequality constraint where you would have some other function g of the coefficients less than or equal to 0. And here, we can have capital M different inequality constraint functions. And so in this case, your objective is you have some cost function j, and you want to find the w that minimizes that, but then you also want to match these equality and inequality constraints. So that's the goal. Let's first talk about the case that you only have equality constraints, so none of these inequality constraints. So there's a really nice and simple trick that you can use in this case, and it is to basically add some additional variables to your optimization called lambda. These are called Lagrange multipliers. So if we have L equality constraints, we need to add L of these Lagrange multipliers. And then what we're going to do is we're going to augment our original loss or cost with this particular term here, where you see that it's the sum of that Lagrange multiplier times the constraint function here. And then now this is our new loss that involves both W and these lambdas, and then we just do an unconstrained minimization over both W and lambda. So at the high level, we started with this equality constrained optimization problem, and we converted it into an unconstrained optimization problem, which is now we know how to solve that. That has some additional parameters that we didn't have before. Okay, so is that idea pretty clear, the procedure? Okay, so the reason that this works is because of one of the basic properties that we know of minimization. So if you have a cost function, let's say, just assume that it is differentiable with respect to this Lth lambda parameter, then we know that when you solve this problem, that the partial derivative with respect to lambda L is going to be 0. But if you look at what is the partial derivative of this cost function with respect to lambda L, it is exactly just this. Okay, so basically by solving this problem and finding the lambda for which the partial derivatives of this go to 0, you automatically enforce that HL is equal to 0, which is the whole goal of the constraint. Okay, so we're just kind of using that zero gradient property to directly enforce these equality constraints. So that's why it works. Does that make sense? Any questions on that? Okay. So when you have inequality constraints, the situation, or let's say both equality and inequality constraints, the situation is the procedure is similar. Here's the original cost. Here's the term we added here. And then here's this additional term where you have some additional parameters. Now we're going to call them mu. And you have your inequality constraints here, these g's. And once again, we now have a optimization problem that's unconstrained, which we need to solve simultaneously over all the w's, all the lambdas, and all the mu's. So in this case, there's some additional complications that one has to check, something called the KKT conditions. But basically, there is a established procedure for doing this. And when you follow this procedure, you can essentially handle this case of inequality constraints. So that's just high level description of how you go about this. And we're not really going to get into more details than this, just to know that yes, this is out there, so that when we talk about constrained optimization later in Unit 7, you can just remember, oh yeah, there's ways to do that, and the way that that's done is, in this case, you add these Lagrange terms and so on. Okay. Yes.
So when we construct these, the constraint function, is there always going to be inequality and inequality? Or?
No, it really depends on the problem. Like some problems, have no constraints. Other problems have only linear constraints. Others have only, equality. Others have only inequality.
Mm-hmm.
Others have both.
Okay.
So it really just depends on the problem you're working on.
Okay.
Yeah.
And then when there's both, this is one of the ways how to solve it.
Yeah, when there's both, this is basically the way you solve it. When there's only equality constraints, it's simpler, and you can do this.
Okay.
Yeah, exactly. Okay, so so those are a few of the sort of advanced topics that if you want to learn more, you can learn about them in an optimization class. There's a few other topics that are interesting and relevant that we didn't get a chance to discuss. For example, like when we did gradient descent, we assumed that we had the same step size on every single parameter that we're optimizing, but you could imagine making that more complicated where you have a different step size on every parameter. Or if you think about the parameter vector as a whole and the step size is multiplying that, you could actually have a matrix valued step size, which is even more interesting and powerful. And when you do that, you get something called Newton's method, which is like a kind of more complicated extension of gradient descent where you're taking the curvature into account in addition to just the slope. You're taking the curvature into account at every step. And just one interesting property of Newton's method is that if you have a quadratic cost function, you will converge to the minimum in one step because it knows about the curvature, it uses it, and it just jumps right to the minimum. Whereas gradient descent has to take this curved trajectory to get there. So that's Newton's method. There's, but it's expensive because you have this matrix valued step size. For that, to compute that, it's the Hessian inverse matrix, so you have to compute all these second derivatives and so on. So there's methods in between called quasi-Newton methods, which are not fully Newton's method, but faster, less complicated, but converge faster than gradient descent. Another thing we sort of saw is that sometimes we have cost functions that are not differentiable, like with lasso, we had that L1 norm. And if you think about for every parameter, that means there's an absolute value, which is not differentiable at the origin. And so you wouldn't be able to use gradient descent to solve it. And so we don't actually really know how to do that. We never discussed it. So it turns out that there are methods to handle optimization when the cost function is not differentiable. Those are also things that you would learn in an optimization course. And furthermore, we until now have focused on convex optimization and things that work well in the context of convex optimization, like the Armijo method. But when we work with non-convex functions like you see in deep learning, you definitely would not want to use Armijo because it would just immediately get stuck in the first local optimum that it found. In those problems, there's millions or billions of bad local minima, and the goal is to try to escape them and to jump into a good local minima. So we have to think about optimization differently. We will talk about that more in future units when we get there. But in case you are interested in diving deeper into optimization, here at Ohio State we have 5500, which is an introduction to optimization taught every autumn. Then we have a convex optimization course 6500, which is taught spring odd years. And then we have a more advanced course that currently has this number, but it's going to get a more permanent number, which is non-convex optimization for machine learning, which specifically deals with this latter issue here. So those are just sort of some plugs for courses that you could take if you wanted to dig more into this. And if you're really interested in machine learning, then this stuff becomes very important to learn about. So that's it for Unit 6. Are there any questions on anything? Okay, great. So let's move on to the next unit, Unit 7. And as a motivating problem, we are going to talk about basically image classification. So, and in particular, we're looking at a very simple and well-known example of this, which is handwritten digit classification. So in this setting, you get a little image that contains a single handwritten digit, like here we have numbers 0 through 9. And your goal is to take that little image and basically treat the numbers, we'll describe all the details, you treat those numbers as the features, and you build a classifier that takes those features and predicts which of these 10 classes that input vector belongs to. So that's the goal here. For this particular data set, this is one of the most well-known data sets for machine learning, just for as an introduction machine learning kind of data set, in part because it's a really nice size. The images are 28 by 28, so there's not that many pixels, 784 pixels or features total per image. There's enough examples that you can learn to do a good job, 70,000. And the history is that this data set was collected by the Census Bureau in the 1980s at the time with the motivation of the Postal Service. Instead of having people, humans, read envelopes, that they would have machines that would be able to scan envelopes and directly figure out what's the address this is going to, so that it could automatically sort mail. And of course, that was done now decades ago, but this was back when they were wanting to do it. And so the first step at that point was just to collect a data set that you could then train some sort of classifier on and actually build that system. So that's sort of where this came from. Even though it's a really old data set, like I said, it's still used a lot as an introductory machine learning kind of toy data set because it's simple, there's many benchmarks, so it's very well understood, and it's an interesting problem, and not sort of a challenging problem, because when you look at some of these digits, it's a little bit hard in isolation. Like if you saw this, would you know that that's a 7? Looks just kind of like a weird digit. And yeah, other ones, like when you see them, it's just not obvious even to a human what that's going to be. So some of these are in fact challenging, like even for humans. So it's an interesting problem to give to a machine. Okay, so that's any questions on MNIST? Okay, so you can get this from many places. Here we can just import it from sklearn datasets. Or actually, no, we're going to download it from OpenML. And when you look at the shape of the data, you can see 70,000 by 784. So each one of these images has been rasterized into a vector of 784, which is 28 squared pixels, and that's how the data comes. So we're going to talk about how you work with that data next. All right. So, and then to motivate the methodology that we're going to introduce in this section, it's called the support vector machine. I'm curious, how many people have heard of the SVM? Okay, a few people. So here is a Wikipedia page on MNIST, and this is not like exhaustive, but what it shows you here is it shows you sort of a leaderboard of different methods that you could apply to MNIST, and then the error rate that you get. And so the best methods here are based on neural networks. We'll get to those in Unit 8. And they're getting an error rate of this best one is 0.17%, which is pretty good, right? It's like 17 errors out of what is that? Out of 1,000, or no, out of 10,000. Right, so it's pretty good. And linear classifier, logistic regression, or this is not exactly that, but it's another pairwise linear classifier. You can see not so good, 7.6%. And here in this row, we have the support vector machine, which is not the best, but it's doing pretty well, 0.56. So pretty respectable method. It's a classical method. It's, not state-of-the-art by any means today, but it has some interesting ideas in it that we can learn about and kind of motivate where we're going to go next. So that's sort of a little bit of motivation about why we're looking at this particular method. Okay, all right, any questions? Okay, so let's talk about representing, how we handle these images. So the way that images are typically handled numerically in NumPy, but also just sort of like any language, the way that they're typically stored is if it's a grayscale image, meaning like not a color image, black and white sort of image, then every pixel in the image has a brightness value associated with it, where a value of 0 would be the darkest possible, black, and often these are going to be 8-bit. They're coded as 8-bit images, meaning every pixel has up to 256 possible brightness values, and no more than that. And this is done because that way, when you store it, it just doesn't take up all that much memory. If you stored this thing as a double precision floating point, that would take up a lot more memory, but it's not really worth it because the human eye can't really see that much better than these 256 brightness levels. Now, if it was a color image, what you would have is 3 different channels. You would have like one of these for the red channel, one for the blue, one for the green. That's the most common way. There's other ways to do it too, but in that case, you would basically have like a triple of these images. But we're going to focus on these grayscale images in this unit. And this is the easiest way to digest this image if we're looking at it as a human. But in terms of storing it, it's quite common to just rasterize this or make it into a vector. And there's several ways to do this in NumPy. So here we're going from, you could think of this as a 2-dimensional array or a matrix of values to a vector. You can use the ravel command in NumPy or the flatten command or the reshape command. And here you're basically telling it, reshape this into a 1-dimensional object, and I don't have to tell you how many pixels to make it because you can figure that out from the current size. So this one -1 is kind of like saying, just use the value, the only value that makes sense. Now, if you want to go back, if you have this representation and you want to reshape it to view it, then you have to tell it exactly what size of a matrix to create from those 784 pixels. And so here you're saying reshape it as a 28 by 28 matrix. Okay, so those are the ways we can go from matrix to vector and back. Now, one thing to note is that different computing languages different computing languages are going to handle this in different ways. Some languages, when you go from a matrix to a vector, are going to do that by stacking the columns. And in fact, if you ever read a book on linear algebra and you see this information, this operation described, which is, it's usually written as vec. You take a matrix and vec will vectorize it. There, the usual assumption is that you're doing this over the columns. Okay, so like so when you vectorize it, you get x1, then x2, and so on, and the very last one would be x784. It turns out that NumPy is a little different. Python and NumPy basically work by doing it row-wise. So if you use one of these commands and you looked at the vector, you'd see this, and then this, and so on. And then after this one, you come to this one, and so on, like that. So it's just something to be aware of. If you want to express what NumPy does in terms of these standard definitions above, you could say vec, and then you transpose this matrix, which basically swaps, flips the rows and columns, and then this column-wise extraction on the transpose matrix would do this in NumPy. So, just be aware that that's how NumPy works. Okay, any questions? Anything here? Okay. All right, and then how do we plot things? How do we visualize things? So the matplotlib library, you guys have been using this for scatter plots and simple like line plots. This also has nice image plotting routines. So the main one is called imshow. So you can see once we reshape this row into a matrix, then we just do plot imshow. And we also want to tell it the color map to use, which is how does it go from numerical brightness values to the picture it shows us. So this is just a grayscale color map, which, the smallest value is black, the largest value is white. You could use some fancier rainbow type color map. Sometimes that's useful for visualization, but in this context, it really makes most sense just to use this simple grayscale color map. And then here it's like we're suppressing the little axis ticks that would normally show up. So that's one thing. Another thing about the MNIST data set, as well as other data sets you might download, is sometimes the samples in the data set are organized in a way that might not be good for training. So in most cases, MNIST, I believe it lists has all the 0 samples first, and then all the 1 samples and all the 2 samples and so on. And so if you said, well, I'm going to just extract a little bit of the data to train a model, and then I'll use the rest to test it, and you didn't shuffle those samples, you would maybe just extract the zeros. And then you would train a model that has only seen zeros, and then obviously it wouldn't work well when it saw other digits. So you just have to be aware that generally speaking, you want to permute a data set once you downloaded it to make sure that you're not taking some structured subset. And so that's what we're going to do. We're going to use this iperm. So and here we're just using it for, here we're just using it to extract random digits for plotting, but you definitely also want to do something like this when you train. So this is creating a list of integers from 1 to In this case, NSAMP would be 70,000. So it's creating like a list of integers from 1 to 70,000, but shuffled. And then if you just take the first element in that list, that's like some random index. Then you can take the next one. That's another random index you haven't seen. Third, and so on and so on. So this iPerm just tells us the order that we're taking the images out of the training set. Okay, any questions? Okay. And so we learned about multinomial logistic regression back in Unit 5. So that would be a very reasonable thing to use as just a baseline. And to save some computation time, we're not going to use all the training data that we have, 70,000 examples. We're only going to use 10,000 examples for training, and then we'll also use 10,000 for test. Now we also have to take care of a few other things, like NumPy doesn't like to work with these 8-bit integers. It generally likes to work with floating point values, so we want to convert x to floating point values. Also, a lot of methods, we talked about how it's often a good thing to standardize the data so that the features have, each feature has 0 mean and unit variance, unit standard deviation, right? Well, if you're working with an image, that might not be the best thing to do, because what's going to happen is you're going to standardize every pixel differently from every other pixel if you use the method that we learned, right? Because each pixel is now a different feature. And for example, in this data set, you'll find that the edge pixels are almost always, or maybe always, black. And so there's no way you can get them to be unit variance because they're all the identical value 0, right? So even trying to do that wouldn't work. But basically, we want to treat all the values the same when we do image processing. We want to standardize all the pixels by the same scale and shift. And so the way that we can do that is we can say, let's just take the full range of our pixels, which go currently from integer 0 to 255, and just warp that range to -1 to 1. That's a very common thing to do when you're processing images. So we want to convert 0 to 255 to -1 to 1. And here you can see the way that we're doing that is we're taking this big matrix of all of our features over our whole data set. That is an unsigned integer from 0 to 255. We are dividing that by the floating point number 255. When you do that division, if one of them is floating point, then the result will be floating point. And finally, so that's going to give us a number from 0 to 1. And then we're multiplying that by 2. So now we have a number from 0 to 2. Subtracting 1, now we have a number from -1 to 1. So that's the procedure. But we have to be a little careful when we do this. For example, it seems like we should be able to do this by multiplying by 2 first instead of last. But if you did that, it wouldn't work, because what happens is if you take these unsigned integers and you multiply them by 2, then things will overflow. So any numbers, any pixels whose brightness is more than half will actually wrap around to have some other weird brightness, because that multiplication is kind of like modulo. So that's why you have to just be careful when you work with these unsigned integers. The first thing we want to do is convert them to floats, and then we can do multiplications like by 2 as we would expect. So that's just a few of the things that sometimes when you start working on this and weird stuff starts happening, you can maybe trace it back to things like this that you might not otherwise think about. Okay, so anyway, so now we have our scale data, and we're just extracting. We have our permuted indices, and this just says, let's take the first NTR, the first 10,000 of them. Those will be our training features, and then we'll take the next NTS of them, and that will be our test features, and the same thing with the labels. The labels in this case, I think I saw them over here somewhere. the labels, I can't remember how they're originally formatted, but here we're basically reformatting them as integers, because I think some of the scikit-learn routines want these things to be integers and not like floating point values and things like that. So sometimes how the targets are formatted numerically is also really important. Okay, so once we've done that, we can just use our regular linear model dot logistic regression and some of the options we're using. So we'll do the multinomial versus the OVR. Multinomial was more expensive, but tends to work better. We can choose which solver to use. Some solvers are faster than others. Some work better with big data sets versus small and so on. So we're using this LBFGS. And we can also tell it how many iterations to run at most, and we can specify that inverse ridge penalty C like this. So, and then finally, so that's logreg, and then we can just fit it to our training data. Okay, any questions? Yeah.
Just two questions. So, was there a particular reason you split the test and training 1-to-1? And the second question is, when you normalize x, why did you convert it to range of -1-1, not just keep it 0-1?
Yeah, it's okay. So the first question, why did we use 10,000 training? That was just a small enough number that it's like enough to get decent performance, but it's not so much that we have to like sit and wait for the computer to run. Okay, the number of test samples is kind of similar, where the more test samples we use, like the better representation of how good performance we actually get. If I use one test sample, like, hey, it might work great for that, but not for other ones. So there too, there's just sort of a trade-off. In this case, we have like 70,000 examples, so we're not really limited. If we were really limited and we were really trying to optimize how many we use for training and test, there's no magic ratio. The most common one that I've seen is 80-20, 80 training, 20 test. But again, that's just one trade-off. The more samples that we use for training, we know that helps with the bias variance trade-off. We reduce our variance. But the fewer samples we use for test, the more we can get misled by our cross-validation type metrics on that test set. So yeah, so these issues will be a very important once we get to the project at the end of the class, and you guys are competing with each other, and you'll see all this in action. Yeah. Okay, and then you had another question about why the range -1-to-1?
Yeah, I thought it would be 0-1.
Yeah. It's a good question. I don't have a precise answer. I think part of it is that this is sort of just typical methodology. If you did this from 0-to-1, I don't think it would break anything.
Oh.
I think it would probably work similarly well, but maybe I don't know. Maybe slightly worse, or maybe the same. It's hard to say.
But it's not a big issue on that.
Yeah, this is just kind of like the standard procedure. So I actually don't know what exactly would happen if it was 0-to-1, like how much worse that would be.
Okay.
But it's a good question.
Oh.
Yeah. Okay. All right. Any other questions? Okay. So let's take a look at what happens then, now that we've trained multinomial logistic regression, and we now can apply it to our test set, and we find that we get a test accuracy of 90%, which, as we know from that table we saw earlier, is not really very good. The best methods are getting less than 1% error rate, or 99% accuracy. So, and when we actually look at specific examples of where we made mistakes, these are just 4 examples that were selected here, where the true digit was 9, but the method estimated a 1. Maybe that makes sense for here because this 9 looks kind of like a 1. This one is harder. I don't know why the method estimated an 8. This looks pretty much like a 4, or why it gave a 3 here, and so on. So it is making mistakes that a human wouldn't make. So it's something as something can definitely be improved. That's the point. And so maybe we can try to figure out, get a little intuition into where, how and why this is not working as well as we'd like. So to do that, let's just quickly review what happens when we do MLR, and maybe we can look at some pictures of this stuff and get some intuition. So this is just sort of a review of Unit 5. This is what we do with multinomial logistic regression, or actually for just any linear method. So what we do is for each class, so this is going to be capital K is now 10. We have 10 different classes. So for K going from 1 to 10, we're going to design our intercept and the weights for that specific class. And basically, like the first BW pair is going to classify X as in class 1 or not in class 1. This is the what we call the one versus rest approach. And this is how things are usually done. So once we design these weights, so that's when we use MLR and we run the optimizer and so on and so on. It's a convex problem, so we know we can solve it. We eventually get our B and W values, and we get them, for all the different classes. And now what we can do is, for each class K, we can compute a score for that particular test vector X. And this is the equation that gives us our score Z, for this K class intercept and weights for our test vector. And once we have that Z, we can, if we like, we can convert that to a softmax, which is going to be a probability value, which basically we can interpret that as some approximation of what is the probability of the true class being K given our test image X. So that's, in some sense, what we do with MLR. And we can, so for MLR, this particular thing is approximated like this. But actually, to do this classification, we don't actually need to compute the softmax, because it's enough just to look at which of all the different scores you computed is the largest, because that is the one that will give you the largest softmax, the largest probability. So computing the softmax is really just something you do for interpretation. It's not something you need to do for classification, because it's enough just to look at the scores and pick the largest score out of the capital K score entries. Yeah, so is that pretty clear? That's the procedure. So here it is illustrated in sort of a block diagram. We start on the right, take our image, we convert this 28 by 28 image to a 784 dimensional vector. Here I'm, printing it as a column vector. And then we can do this multiplication W transpose times X. So if you think about like what happens in the first Z here, that's going to be the first intercept term plus an inner product between the slope coefficients and X. So that is essentially doing this. And we do that separately for each of these different scores, and we have 10 scores total because we have 10 classes. And if you like, by plugging those numbers into here, you get a whole vector of probabilities that actually you can think of as a probability mass function, which is a distribution across the different classes, where you would see, oh, this class, I think it's this class with 80% confidence, I think it's this one with 10%, and so on. So you actually get some soft outputs here, which are more informative than just saying the most probable class was, class 7, for example. Okay, but anyway, that's how it works. Any questions on this? All right. So so if you take a look at this equation is kind of showing you how the weights combine with the test image to give you the score, which is the really important thing here. You can see that it kind of comes down to this. There's an inner product between the image and the weights. So here, this is the rasterized image and the rasterized weights. If you reshape both of them into matrices, the way you can imagine it is it's just like a pointwise multiplication between those two matrices, the matrix of pixels and the matrix of weights. and then you sum all the values. So we saw that in the form of trace X transpose WK. We saw that that was the inner product for matrices, which, yeah, exactly what happens is it's just a pointwise multiplication between matrices and then summing the values. So that's another way to understand this. But from that logic, you can see that in order to get Z really large, which is what we want Z to be large for the correct class, right? Because the largest Z is the one we choose when we classify things as a particular class. So we want that WK should resemble X, because when those things have the same sort of pattern and you do this multiplication and sum up, you get the largest output, right? You want them to be kind of aligned in that way. So in other words, when we actually plot these W vectors after reshaping them into images, we hope that like W0 looks like a 0 image, W1 should look like a 1, and so on. And in fact, this is kind of what happens, but let's do this a couple different ways. So let's first imagine that instead of using our 10,000 training examples, we only use 100 training examples. Then, so we get these W's and B's, and now we're reshaping the W's into images and plotting them. And you can see, yes, the W0 weights actually do kind of look like a 0. So in terms of this color map, I'm thinking that probably this color gray is the numerical value 0. This color black is probably a negative numerical value, and then this white is a positive numerical value in W. So I think that's what the colors mean here. So you see a 0 in the W0. In W1, you see what looks like a 1. In W2, you see what looks like a 2, and so on. So things seem to be kind of working out, right? We're essentially doing sort of a pattern match between this and X. And so when X itself looks like a 2, the Z is large, and that should, tip us off that, oh yeah, that's the class that the image really is. So, so everything works out pretty well when we do this with 100 training samples. But a strange thing happens when we do this with the full training set. We get these pictures for the weights, which now you can see that it's quite hard to see the zeros and the ones and so on in here. This looks just kind of like a mess. I mean, yeah, there are certain values in these weight vectors that seem to be 0, but like the interesting ones, they look almost random. So what's really happening is these coefficients are picking up on very strange patterns within these, that it saw within the training set. And it's using these very weird patterns to come up with its answers. So it almost seemed like in going from a few training samples to many, it's almost kind of getting confused with maybe it's, somehow it's not focusing on the right training examples to make a really nice W vector. It's somehow getting distracted by things in the training set. Maybe it's sort of overfitting or something. So the question then is there some method that escapes this? So is there a way so that when we train a method, we can focus only on a few important training samples and not get distracted by all the ones that don't really matter? Like maybe when determining that there's a 1, there's particular training samples that I should be paying attention to because these are the challenging ones, and then maybe all the easy ones I just ignore because they're not really helping me at all. It's really the ones close to the decision boundary which I should focus on. So that is the spirit of this whole unit, is can we come up with some methods that instead of using the full training set, they automatically filter out to find the most useful training samples, and then the design is based only on those. So this is sort of just a motivation for doing that. Okay. Is that making sense, what I said? Are there any questions on anything here? Okay. So that is going to be kind of the guiding light. So the methods, the support vector machine, and the ones that lead up to it are all going to be, at the end of the day, doing this. They're going to be focusing on a few important training samples, and those things will be called the support vectors. So that's where the name comes from. Okay, so it turns out that there's like a couple versions of this that we have to get through before we get to the final method. So we'll just build things up slowly. And what we're going to first do is just go back to really the fundamentals of linear classification, and in particular, all the things we can learn about the decision boundary itself, many of them just from studying this plot here. So in this plot, we have a case where we have just two features, x1 and x2, and you can see we have some blue samples, some red samples. So clearly, if we put the decision boundary here, that's a good place to put it because it's separating the red from the blue. But what we're interested in now is noticing or learning a few things about the weights W and the bias B that we can get just from this picture alone. So the first thing is that, and you saw this in the homework due today, that the decision boundary, which is this line here, decision boundary we can write, let me use a thinner pen. Okay. Oops. The decision boundary we can write as the set of x vectors such that B plus W transpose, or maybe I'll write X transpose W equals 0. Okay, so where does this come from? Well, remember that in linear classification, this quantity, B plus X transpose W, this is the score Z associated with this input vector X. And we know that when Z is 0, that is right on the boundary between saying that this X should be in class 1 or not in class 1. So this is like the most uncertain case, and that is right on the boundary. That is, we know when Z equals 0. So that's kind of how we're getting this expression here. So so the set of points, all the set of x1, x2 pairs here satisfy this equation. Okay. Okay, and this is a hyperplane, meaning in now with two features, it's a line. If we had 3 features, it would be a 2-dimensional plane. If we have 4 features, it would be a 3-dimensional plane, and so on. So in general, this is called a hyperplane, which is sort of like a plane, but in any number of dimensions. Okay, so so the first interesting result is that this hyperplane, this thing, is orthogonal to the vector of slope coefficients W. And so here on the diagram, you can see that this is the plane, and then here, this is an orthogonal line, which is at a right angle to it. So, okay, so this is an important thing. So question is, okay, why is this? How do we get this? So sort of as a short proof, we know that, for all the points on the boundary, this has to hold. So if you take any 2 points on the hyperplane, so maybe a point x1 and a point x2. Now these are boldface x, meaning don't confuse that with the scalar x1 and x2. This is one example of the x vector, another example of the x vector. If I have both of them on the hyperplane, then I know that each of those must satisfy this. So I would plug in like xi there, and this equation would hold, right? Now if I take those 2 equations, and I sort of think of it as a system of equations, B plus x1 transpose W equals 0, B plus x2 transpose W equals 0. Well, if both those equalities hold, then I should be able to subtract both sides of the equation, and it should also hold. And you can see that if I subtract the bottom from the top, I get x1 minus x2, that quantity transpose W equals 0, because these b's cancel, and when I subtract the zeros, I still get 0. So we get this equation here. And now if you just look at this equation, it says that the difference vector, so if I have 2 points here, their difference vector is exactly in line with that boundary. That transpose W is 0, which means that that difference vector is perpendicular or orthogonal to the boundary. That's what it means. Orthogonality means that the inner product is 0. Okay, so hopefully this convinces you that yes, W is orthogonal to the decision boundary. Any questions on that? Okay. Another thing we can notice on this diagram is if you, so for example, let's say that I show you a picture like this picture and I ask you, okay, exactly what are the W and B coefficients? Okay, so you know from this picture, W must be orthogonal to this, so that kind of gives you a clue of what W must be. Now, you also notice that I can scale W by any value, and I'm still going to get orthogonality. I'll still get this hold. So I can tell you what W is up to a scale factor, but I can't tell you what that scale factor is. So I can just tell you, like, W is proportional to, you know, these two numbers. Now, likewise, if you said, well, what about B? What is the value of B? Turns out just by looking at where the boundary crosses the coordinate axes, you can figure out what B is. So, and this holds because, again, from this equation here, if I'm on the x2 axis, then on that axis, the x vector has the form 0, comma, x2, right? Because along, all the way along here, x1 is 0. So that implies that B plus x transpose W is 0, but x transpose W now, plugging in this particular x, is just going to be x2 W2. Right? There's this 0 kills the W1 coefficient. And then lastly, if you're saying, well, what value of x makes this true, you just bring B to the other side, becomes negative, and then you divide both sides by W2, and you find the value of x2 right here is minus B over W2. Okay, so that's where that comes from. Minus B over W2 is x2. So just if you see a picture of this, and we can do everything here, but with x2 replaced by x1 to figure out this point. So if I just show you this line, and you can figure out what these are, you can immediately figure out what B, W1, and W2 are, all up to an unknown scaling factor. The scaling factor is impossible because you can see if B and W2 are scaled by the same amount, that doesn't change this location. Same thing here, doesn't change this location, nor does it change this orthogonality. So you can get all three parameters up to a scaling. To figure out that scaling, you need to go farther. You need to say, well, okay, if I'm doing, there's ways to get the scaling for particular losses. Okay, so that explains these. Any questions on the intercepts? Okay. Okay, another important point to talk about is how close a given point is to the decision boundary. This is important because basically, the closer a point is to the decision boundary, the less confidence you have about its class, right? As you get close to that boundary, you're less and less confident. So these points out here, you're quite confident those are in the red class. These, you're quite confident that it's in the blue class. The ones right on the boundary, you have no idea what class it should be in. So the distance to the boundary is an important quantity that tells you how confident you should be about a given point. So let's compute, let's come up with an equation for the distance from a point. Let's say this point, we'll call it x, boldface xi. How close is that to the boundary? So to figure that out, we can again use this equation, and we can write it this way. 0 is b plus, and then I'm going to have xi minus, I'll describe this in a moment, gamma I times w, the w vector over its norm, transpose w. Okay. Okay, so this is a unit norm direction vector. That's what, if you divide w by its norm, you get a new vector that has norm 1 or length 1, but it is still pointing in the same direction as w. So we'll call that a direction vector. So if I take that unit norm direction vector and I multiply it by a scalar gamma I, now I have something pointing in the direction of w with length gamma I. So the question now is, okay, I start at xi. I'm moving exactly in this direction, which is in the same direction as w, right? Because if I want to measure distance to the boundary, I want to move directly towards the boundary. I wouldn't want to say the distance between that and the boundary is this much, right? Because no, like we want to measure distance according to what is orthogonal to the boundary. And we know that w is orthogonal. So that's why we're moving in the w direction. We're asking the question, how far do I have to move, gamma I, to get to the line? Because at the line, I know that I get 0. So what we need to do is we need to solve this equation for gamma I. That says how far we need to move to the line. So that is where this is coming from. Is that making sense? Or any questions about that? So one thing I should point out is that this is actually a signed distance, because from this point I could move in this direction or this direction. Right? So both of them, they would each have a separate sign. So here we're saying we're moving in the negative of this direction by that length. So when we compute this, we're going to get a gamma I that's not like a typical distance that's always non-negative. This distance will actually have a sign on it, and it's going to tell us which way to move. So if I'm over here, I want to move one way, but if I'm on this side, I'm going to move the opposite way. So this is what we're starting with, and now we just want to derive an expression for gamma I. Okay. If there's no questions, we can just move on to a slightly different way of writing this, but are there any questions about this overall idea, how we're measuring the length, by how far we need to move to get to the line? Okay, so let's just rewrite this then as b plus xi transpose w. And let's look at this last quantity here. So in the numerator, I'm going to have w transpose w, but that is the squared Euclidean norm of w, which I'm going to divide by the unsquared Euclidean norm. So finally, I'm going to get minus lambda I times the unsquared Euclidean norm. Okay. And the last step is easy. We now have this equation. We just need to extract gamma I from there. So we bring this to the other side. We divide by the norm of w, and you find that this is the expression for the signed distance from a point to the hyperplane is this guy here. Okay. So, any questions on that little derivation? Okay, so now given any training point, you could plug it into this expression knowing the coefficients, and you could say, oh, that's exactly how far that is. Okay. The last thing on the slide is something I kind of talked about. So if you give me a classifier parameterized by an intercept and weight vector, and I multiply that by some positive number, I multiply both by some positive number alpha, you can see that the location of the decision boundary does not change at all. All that changes is the size of, if I scale both of these, the size of z will change, but where the boundary is doesn't change at all. So sometimes we call this scaled classifier it's equivalent to the original one in the sense that they have exactly the same decision boundary. Now, if you use a negative alpha, what happens is that has the effect of flipping all the red and blue. So that actually is it's changing the sign on z. So you don't want to do that. You want to, we say it's equivalent if for any positive scale, we scale it. Okay, so that's the last thing. Okay, so that's definitely it for today. Sorry I went on a little bit long. So we'll continue this discussion on Monday. Hope you guys have a good weekend.